Yeah, no. I still in the street.
All right, today we're going to be talking about encoding schemes, and we're going to solve the problems of lack of synchronization or picking up the better scheme. So hopefully today onwards you should be able to pick up the better encoding scheme that's available. And I'll just go through some of the material that you already have been through, but either I'll remind you or hopefully I might teach you something new. And then we move on to something called scrambling. And scrambling is the actual scrambling technique that's used to improve encoding of data or transmission of data. So let's work it out now if we can. Right. So you can stop me anytime and ask me questions if you like. All right. Right, the usual or the basic technique for encoding data is to have lots of ones and zeros in your memory and you want to send them, is maybe to pick any two values.
I think it's from that stuff.
Is this better? Yeah. This is really good. Put it back on and see.
No, it's better without the light.
Okay. Yeah. Right, and maybe changing the color might improve things a bit as well. A slightly different color, yeah. Okay, so for example, we pick any two values to represent the bits. This is the most basic technique used. So usually there's a value that's flowing, maybe it's a 0, but every time there is transmitted data, maybe we increase this if it's 1 to +5, and 0 is represented by -5. And there, that's the way the signal might look like if we plot the voltage or the amplitude of the signal. And there's nothing wrong with that, that's perfect. It has a couple of issues with this that if we can improve it, it'll be great. One of them is error detection. If a bit, when transmitted, for example, this might have been a 0, but when transmitted, it appeared like 1 to the receiver. Maybe the sender was sending 100, but we got 1 and a 0, and then instead of another 0 here, we received the signal changed to +5. Can this be discovered by the receiver? Unfortunately, there's no way of telling any of the bits here if they have any errors. Any bits could have been reversed during transmission. Like, there's no guarantee this second one is actually a 1. Could have been also another 0 that flipped into 1. There's no guarantee that this 0 could have been a 1 that was sent by the sender, but the receiver received it as a 0. So that's one issue that schemes cannot detect. A lot of schemes cannot detect an error. So just to solve that issue, that problem, is an alternating AMI. If you've heard of that, forget about the 0. They should just concentrate on the 1s and flip every time. So they don't have a fixed value for value 1 and fixed value for 0. They have actually identify 1s as by switching the values from +5 to -5. So 1 is represented by +5 or -5, alternating between them. They said this might be a better scheme. So how does that work? If we start, and the first one, we give it a +5. The next one is a 0. So we say it's 0. 0 does not have the value -1. It has the value 0. Now, if the next value was a 1, now we go to an alternating. So this is 1, that's a 0, that's another 1. So every time we get a 1, we go to +5 or -5. +5, -5, alternating between those two values. Now, the next bit is 1. It will go to +5. The next one is another 1. We go to -5. The next one is a 0. We flip to 0. The next one is 1. Where would I go from here? +5 or -5 for the next one? +5. And the next one is -5, and so on. So this is known as the AMI, alternating AMI. So how does that do? Is this better? Yeah. Imagine if one of the ones changed, and instead of, let's say this one, when transmitted as -5, it arrived as +5. So now the receiver say, okay, I have +5, that's a 1, that's a 0, that's another +5. Hey, I can't have 2 +5s, 2 consecutive 1s. There must be an error. So in this technique, you can actually discover some of the errors. If a 1 flips from +5 to -5, -5 to +5, it would discover it. Also, if a 0 flips into the wrong place, it would be discovered. If a 0 becomes a +5 or a -5, it would be discovered. How would it be discovered? Let's say if this 0, instead of showing us 0, it changes into +5. If it changes into -5, then we'll have 2 minuses, any consecutive similar values that will indicate an error. If it flipped into a +5, we would not discover it immediately, but because there is another +5, we'll discover it at the next bit of 1. So this has a reasonably good error detectability. Alternating AMI. Another issue that faces these encryption schemes, that if we have, again, let's go for 2 values, for 1 and 0, let's go for +5 and -5 again. So if we have a 1, it's a +5, and a 0, we go to a -5, for example, and then another +1, 1, 1, so it remains a 1 for a while, and so on. So it can go to a 0 and keep switching around. Now, the problem with this, if we get a long string of 1s, there's no change That's when we have the problem of synchronization. Synchronization, or the lack of it, synchronization, that means timing is good, but lack of synchronization, that's when we start losing timing. So the clock of the sender and the clock of the receiver kind of start getting out of sync. Not the clock, but we call it clock or timing between them, or in fact, the bit period. So the bit period is, say, a millionth of a second. The receiver goes a little bit over a million. So after a few 10 or 15 bits, it would gain an extra bit or to lose a bit. Tiny, small difference, but it will build up over a few bits, and then we have what's the out of sync problem. They call it synchronization problem. So the two of them are not in the same synchronization. This is a major issue in communication. So there are many ways to do it. And one technique is the Manchester encoding, which you've already covered. We'll have a quick look at it. The recording should be full in here, sorry. Just try something else here.
It's really just a line.
Share. It's not going to stay this way, so I'm not going to see much on the screen. Maybe if I change the camera, it will work.
No, I don't know, like, this is something.
And so it should remain. Okay. That's better.
That's a problem with this.
Okay, the Manchester encoding. First, something you need to know is that the receiver always lines itself with the sender. And it's the only, well, the easiest way it does line itself if it notices a change. If there's a change from +5 to -5 or from 5 to 0, it will know, oh, like it'll feel it, it's easily felt. And at that time of the change, the receiver, if it was a little bit lagging behind, it will go a little bit forward. Or if it's already ahead, it will slow down. And so the receiver can always line itself with the sender at the change of a power or you know, the plus or minus, if there's a major change. So, and that's why with these, because there is no change, it's almost, they call it direct current, continuous current at one certain value, then that makes the receiver gets out of sync. So the Manchester encoding, they came up with this idea, is that maybe we can, if we have a clock, so if we have a clock signal that keeps, the clock signal is something that keeps changing, ticking all the time. And it ticks many times a second, as much as fast as we want. So, and now if we have the data, then we can have the data. For example, we're sending 1 and 0, so we can send the data. We might have lots of -5s or lots of +5. And what the sender does, it XORs them together. So it will force the resulting signal that's going to be sent is that it's always going to be flipping, or at least it will make one flip at every cycle, at least. Sometimes it flips twice in the same cycle because the clock signal is forcing it to change. But as we now are sending, we're not just sending data, we're sending data and clock together. So the data has been changed. And we'll look at the exact details of how does it actually change. But the receiver will need to take this signal and separate the clock again from the data, and then can read the data. But at least we make sure, using the Manchester encoding scheme, is that we're flipping every cycle. Every cycle there is a flip of the power. So the receiver can always line itself up. They will never ever have continuous for more than one cycle, which is good enough. Sometimes actually in every cycle it flips twice. But it's the best scheme, in keeping synchronization. But the problem with it is that it's too expensive and too complex. This extra signal that we are sending is going to take part of the overall bandwidth of the channel. So the channel can transmit certain amounts of data, but now you're not just transmitting data of user information, you're also transmitting the data of the clock. So those two data, then the clock data is taking part of this channel capacity and is reducing the overall user data that's transmitted. So the cost is quite high with Manchester encoding for two reasons. The first reason is the bandwidth reduction, that we cannot send the same amount of data now because we have to send the clock. And the second part is the extra complexity and extra cost of the device. So the device guarantees absolute synchronization, but at a very, very high cost. And therefore, Manchester encoding actually is no longer used. It's been done with many years ago. It was used for a short while. It gives fantastic synchronization results, but the cost is too high to make it usable. So that's the way, one solution to have with the Manchester encoding. But the alternating AMI still gives the next best solution to that. It will eliminate any continuous string of ones, but if you have long string of zeros, it falls on the same, it has the same problem. It cannot alternate zeros. So it's good only for getting rid of the synchronization problem, but it can be caused by long string of ones. But long string of zero is not done, and that's why using this technique with the new technique that's called scrambling. So scrambling is a small technique that's used just to solve a problem of many continuous long string of zeros. The scrambling comes in, finds long string of zeros, replaces them with special code that normally does not appear, and the receiver knows, oh, that's a code. What does it mean? It means there should be lots of zeros here. So it replaces them with zeros. It's so intelligently done that you solve the problem at no extra cost. If you're transmitting 10 zeros, you're still transmitting 10 bits. So we're not consuming any part, we're not transmitting any redundant data. And it solves the zero problem. And therefore, this combination of the alternating AMI scheme plus with the scrambling, it just solved all the issues. It solved the complexity. They're not complex, they're reasonably quite simple. And they solve the problem of the bandwidth. We're not really using any more data than the actual user data. And they provide error protection, and they provide synchronization at a low cost. These are the actual factors that are checked when you want to evaluate encoding schemes. These are the factors that you need to check. So every now scheme we go through, we check, does it provide error detectability? Or if you're given two schemes to compare, then you check those two schemes, which one is better? We check. Do they provide error detection? If one of them provides error detectability and the other does not, then obviously the one with the error detection is better at no extra cost. Now, Another thing that we check is the noise immunity. The noise immunity is if the channel is not so clean, and if there's other noise, that does our system, does this transmission system, can it work and extract the correct data and deliver the data the correct, despite some noise that's already in the channel. So one way to look, the way it's done, it's done in some schemes by taking differential readings, not taking one absolute value. The absolute value sometimes is not very accurate. If, for example, again, the two values are +5 and -5, for example, or +5 and 0. Let's say you get +4 and -2 instead of -5. Some schemes would not work. They would not identify, oh, that's not -5, it's gone. But, and again, so this would be +5, this one -5, but sometimes noise is when you do not get the exact signal as expected, as was sent. So one of the schemes that was implemented actually in Manchester encoding scheme, it takes 2 readings instead of 1. So most of the schemes, the way they operate, they come to the bit period and they take the reading right in the middle. They say, imagine we're sending 1 million bits per second, but each bit, they say, don't measure it at the start, measure it in the middle part of the bit. You're really talking about now 1 millionth of a second, and you're going halfway along the 1 millionth to take the reading. That's where the readings are taken. But sometimes that's not necessarily a good reading, and if these two are so close to one another, the receiver would not know. They're too close to home. They're not too close. They say this one is way away from +5. I don't know this value, and it's not a negative, and this one, it's negative, but it's way too far from -4 or -5. So what Manchester did, they say, listen, instead of taking 1 reading, take 2 readings. So they take 2 readings, 1 before the switching and 1 after. And so 2 readings at each point. At the end, just before the changing or the bit period, they take 1 reading before it and 1 reading after it. And depending on the distance or space between those 2 readings, they decide whether it's the next one is on the other side or closer. So this one here and this one, there's a huge difference between those 2. They say, okay, there is a change. The last one was a plus, and this one, even though we weren't able to determine it, but we'll take it as -5, and so on. So, and then if they take the reading here, -2 and +5, say there's enough space difference between them, we know a change has happened. So they found this is called differential reading. Differential readings, take 2 readings and check the difference between them, and that's one scheme that overcomes the noise. So differentials readings improve or overcome the noise, immunity to noise. This makes this system immune to noise. Immune to noise, I mean, it's not 100% noise proof, but it will work even, when there's a lot of noise in the channel. So immunity to noise is solved by actually by the differential reading bit. How is the synchronization problem solved? Or lack of synchronization? How did we solve the problem of just 1 continuous 1s or 1 continuous 0? Using a clock is one technique, or using the alternating AMI technique where you change the 1s In some schemes, they used it to change the 0 and leave the 1. But either way you do it, you're only solving half of the problem with the AMI. The clock definitely solves the synchronization problem, but at such a tremendous cost that it was not usable. The solution using the clock was really, left out. It increases the cost and makes the complexity, whatever. So cost and complexity, most of the time they work together, or they're both checked as factors, cost and complexity. If the device becomes very complex, then it becomes very costly, very expensive to install these devices, transmitters and receivers. Also bandwidth, the simplest original schemes are the best. They don't have clocks, they don't have extra data, and they only use 2 values, plus or minus, or plus and 0. And AMI, alternating AMI, is still reasonably maintains exactly the same bandwidth, especially when scrambling is introduced. Noise immunity, how is it solved or sorted out? By multiple readings, and it's known as differential. Error detection, how is error checked? Yeah? By alternating ones, alternating signals for ones or zeros. And if you get the same value more than once, if it repeats itself, then we know that there is error. So these are really the factors that you need to remember, and you should have come up with from last year, is that those encoding schemes, they can be compared to one another, and these are really the factors that are used to compare them. So if you're given any 2 encoding schemes, let's say the famous ones, Manchester encoding, that uses the clock, you can say, all right, that solves the maybe synchronization, but the cost is too expensive and complex devices, and you're joining 2 signals and separating 2 signals at the receiver, that it wasn't worth it at the end, and it reduces the bandwidth. So we're going to look today at the AMI alternating scheme that solves, continuous ones, and then which you should already know, but we'll add to it scrambling. So today we're going to be doing that and the scrambling to solve both problems. Yeah.
Sorry, what did you say solves bandwidth and cost?
The cost is just keep a simple device, like by adding a clock, by adding 2 data, 2 devices, joining 2 signals together and separating them needs extra complexity in the design of the device itself, and that makes it more expensive.
What about bandwidth also?
The bandwidth, just reduce, don't get a solution that will generate redundant data. Remember, redundancy is, for example, you are sending 1 million bits. How many extra bits do you have to send by your solution? As we will, maybe later on, we'll do error detection, that you'll find different types of error detection systems. Some send 10 bytes with every packet, and some send, 1,000 bytes with every packet as part of the solution to make sure there's no error. Of course, though, if you're sending data, it's like an airplane that's taken off with 100 passengers, and they have to carry all the weight of those 100 passengers, but it needs to take fuel, and the fuel has weight as well, and that's redundant fuel that needs to be carried. Unfortunately, it's an extra cost. So any device, any service you get to deliver something, like in communication, if you had to deliver 1 million bytes of user data, how much extra do you have to send or transmit with this 1 million bytes? whether it's an error detection, whether it's routing, whether any scheme, any of the applications that are used in communication, if somebody comes up with another app or another application or another protocol that will produce less redundant data, then it will be adopted. So in the case of the synchronization, the clock is really a bad thing because it's gonna eat a lot of the space that's used for transmitting. You're gonna transmit the user data and also the clock data. So that's what really ruined the synchronization or the bandwidth of the material. And any other scheme, if there is another scheme that will send more information in order to help with the error detection, well then that will be extra redundant data. Right, so let me put the slides on and we go through the slides. All right. So we look at the encoding technique concepts and the encoding scheme. So some of this material you may have already seen or used. So I go fast enough. If you have a question or anything not clear, just ask away. I'm assuming you've done this. So first we're going to be moving to the encoding of data. Talks about here digital and analog data or signaling. The digital signal is a sequence of discrete, non-continuous voltage pulses. So that discrete, that means there are only two values, and we know what the two values are. The analog signal is not discrete, it's continuous and variable. It can have any value. That's one of the major differences between digital and analog. Each pulse is a signal element. Binary data are transmitted by encoding each data bit into a signal element. So whatever the signal element is, could be frequency, or it could be amplitude, voltage, or it could be a 0 or 90 degree, or and in the simplest case, there is one-to-one correspondence between bits and signal elements. So maybe 1 cycle per bit. Sometimes we can do more than 1 cycle per bit. Signals are either uni or polar, or unipolar, or full polar. Unipolar, that means it only uses one part of the electromagnetic or the electrical part of the signal. Remember the cycle that goes from +5 to -5 to 0 as the angle changes. In some schemes, they only use the part above 0, +5 to 0. They never go near -5. And others, they use the full polar part of it, both poles. Polar is in the positive or the negative poles of that representation of the cycle. The signal rate is the number of bits transmitted per second. The duration of each bit is the bit timer, or there's another name, length of the bit time. Encoding schemes There's a signal, there's the clocking, these are noise immunity. Noise immunity is that being able to operate in a noisy channel and still recognize the differences, and that's done by multiple readings or differential readings. Error detection is done by the alternating part. This is, you need to really know this, because these are the kind of questions that we'll be concentrating on in this part or level of your course. Cost and complexity. Anytime there's an extra device to be, the device gets more complex, there's going to increase in cost. Signal timing or clocking. This is the determination of the beginning and the end of each bit position. That's when does the bit start. As far as the sender is concerned, as far as the receiver is concerned, they should always, the bits start and end at the same point of time, but synchronization where sometimes they go past one another. And here's an example where a sender and a receiver might lose track or sync of each other, and that will generate extra bits. So if the sender is sending 1011 and the receiver kind of starts reading them a little bit quicker, might end up getting 110 and so on, 111. So they start getting wrong signals quite short, very short time. Because we're talking about 1 millionth parts of a second. We're talking at that level. They need to be really quite together. Error detection is already provided for by a layer of logic above the signaling level. So at layer number 2, the data link layer or the network layer or end-to-end, level 4. But usually the signaling at this level, at the physical level, was never really at a technology where they also provide error detection. But they started recently, and it's a useful material if we can have it. And if we can do all the error detection during signaling at no extra cost, we can remove it off the next, the higher layers. For now, it's in both. So it permits faster error detection if it can happen at the noise level or the signal level. Noise immunity encoding schemes differ in their ability to perform in the presence of noise. Obviously, we prefer if the transmitters and receivers will still work even if the channel is not that, if it's noisy or there are other transmissions. But it's not easy, and it probably costs a lot as well. But it's measured in networks by how many bit errors per hour or per minute or per day or whatever. So it's a rate of bit error. That's you can measure how clean channels are. Cost and complexity. Despite the falling prices, cost is still an issue, and typically the higher the signaling rate to achieve a given data rate, the greater the cost. And encoding schemes can require a signaling rate that's greater than the actual data rate. So this is a good example of that is the Manchester encoding. It can transmit a lot more, but it's not all user data. And that's unfortunate. So these are the schemes or encoding schemes that I know you should have looked at last year. So we'll have a quick look at them. They're quite simple. Well, we won't need to go into details, but you're expected to know them because we're going to build a scrambling on top of at least one of those schemes. So let's look at those. Now, return to zero scheme is a simple scheme that you have two different voltages, and the voltage is constant during one bit for 1 or 0, and there's no zero. The zero value of the signal is not used as part of the transmission. They call them non-return to zero. They never go to zero. if you, for example, 0 is represented by +5, for example, and 1 is by -5. That's it. +5 for 0, -5 for 1, and these are the two levels. So they never go to the 0 level of actual voltage. The next one, that I think only changes if there is a 1. If there is no 1, there is no change or something like that. So I'll return to 0, inverted. So we have a 0 at +5. The next one we get 1, we go to -5. If we get a 0, we don't change. 0, no change. We get a 1, we go to +5. Another 1, -5. So this is the inverted at the 1 bit. It just changes the value at 1 bit. Otherwise, the 0, no change at the 0. It doesn't go to 0. It just no change where it stays where it is. That's another scheme. So there are a couple of schemes known as the non-return to 0. They never use the 0 signal part. There are other examples as well that they change, they force a change at the, once you represent the 0 by +5, for example here, and 1 by -5, but they return to 0. So halfway through each cycle, the signal flips to 0. This is returning to 0. So everything goes and indicates the 1 or 0 and come back to the non-voltage value. So for example, the next one is 1. 1 is represented by -5. Go indicate -5 and return. The next one is 0. Go up to indicate +5 and return to non-voltage. That's the return to 0. It forces multiple flips, these two flips in each bit. It's not easy technology, so it's rarely used. So non-return to 0 and non-return to 0 inverted are easily engineered. They make good use of bandwidth. They don't waste any bandwidth. They transmit exactly what bits you have, and they don't transmit any more. So if you give them 1 million bits, that's exactly what they're transferred, no more bits. So they're the best kind of the cheapest way of traveling, but they're not the best because of the long 1s or 0s. Disadvantages, they have this problem that causes the synchronization. It's called the DC component, direct current component. Because if we get long 1s, few string of 1 bits or 0 bits, they will take that +5 or -5 for a long period of time. And that causes lack of synchronization. So this is really the main issue with them. Otherwise, they are efficient. They use their channel very efficiently, but they suffer from the direct current component, which causes synchronization. Let's keep going. Differential encoding. That's when you start taking 2 readings. This is an improvement to noise, to overcome noise. Non-return to 0 inverted is an example of a differential encoding scheme. The signal is decoded by comparing adjacent signal elements. So taking 2 readings. You don't just read once each bit, you make 2 readings. One just before the bit change and one after the bit boundary. So are they close to one another? And we assume they have the same value then. Or are they too far? There's enough difference between them to say, oh, that must be the opposite value. They provide good noise immunity. So differential encoding provides good noise immunity and does not lose the sense of polarity, as polarity is relative to adjacent signals. So it's basically a much better improvement Remember, always the others you measure, you in the plus side or the minus side. And it depends a lot on the differences in the voltages between them. At least with taking one reading, sometimes you're not really too sure, but when you take the two readings, even if there's slight difference between the plus and minus, you can sense it, and this way you can assume the value. So if it's -1, you can say, okay, it's -5, you know, it was -5. In the other types, -1 might be missed completely. So, no, that's way too far from +5. But if the one before it is a plus, well, then you say, yeah, there is a change from plus to minus. We'll assume it's a change. So it will keep working even if the noise, if the channel is not correct. Multi-level encoding, that's taken more than one level. There are schemes that take a lot more than, you know, those 2 or 3 readings. They take many different levels. They can measure 1 volt, 2 volt, 5 volt, and they can transmit more information, but they get into the complexity issue. So that's another issue of complexity. If we have a device or a manufacturer say, okay, I have a transmitter, I can transmit and identify multiple levels of voltages. Yeah, it's great, and maybe you'd be able to transmit more data, but it makes that device extremely expensive. So the bipolar AMI alternate inversion, the 0 is represented by no line, 1 is represented by positive, and 1 represented by, and the next one is by negative, is probably the best scheme that's there. So let's go through, look at this one. Oh, pseudo ternary encoding is the comments of the same as the AMI, bipolar AMI, but in reverse. Each one introduces a transition, and the 0 does not. The 0 goes to 0 level, or the bit 0. So better look at the diagram. Let me go to this one. This is the pseudo, no, this is the initial one, which is the AMI inverted, or alternate mark inversion, AMI bipolar scheme. Bipolar, it uses the plus and the minus, and AMI is alternating each time it gets the value 1 or 0, but we'll stick to the 1 now. So here's the scheme. The 0 has no signal or no value, that's value 0 in the actual scheme. If you get 1, we go +1, provided the previous one was a minus. So now in this scheme, you need to know what was the last value used. The next value is 0, we just continue with no voltage. The next one is 1, okay, the last one was +5, we go -5. And hence the name bipolar. So bipolar means we're using both signals or signs of the pole, of the frequency, or not the signal that's shown here with +5 volt and -5. So another one, so each time you get a 1, you just change, flip. So it's great if our data was 1s or long 1s. We'll never have direct scheme. But the pseudo ternary, I think it's just the opposite. I think it uses the 0. So let me see if I can get this right. This is the normal one we are looking at, the bipolar AMI. The 0 is represented by no signal. The 1 just flips from plus to minus, another one plus, another one is minus. The pseudo ternary, the 0s will take the plus and the minus, and the 1 will take no signals. So the 0 takes +5, the next 0 -5, next 0 +5, next 0 -5, and the 1s take the no signal. So this is just the opposite representation of this one. the bipolar AMI. You need to know, you need to be able to plot this if you are given a string of ones and zeros, the bipolar AMI or the pseudo-ternary. Pseudo-ternary is just the opposite, reverse the ones and zeros, but we will concentrate on the bipolar. That's the main scheme. If you have any string of bits here, the ones, the zeros, just start with 0 is always no value, and the ones, they go up and down. You always need to know what was the value of the last one. Did you give the last one the previous value, a plus or a minus? If in a question you are not given the value, you make an assumption. You say, okay, I'm going to assume the last one had a -5, for example, and then your answer will read it from there. So what's good about this scheme? It's very simple. So it's not complex. It does not send any more data with the user data. So it utilizes the channel extremely well. It does not have a synchronization problem in the case of, and the top one, if we have ones, long string of ones will not cause us any problems. We still have problems with the 0. The bottom one is the other way around. So let's just stick now to the bipolar AMI. This goes through the Manchester encoding scheme. I mentioned it earlier on. This is the one that solves the synchronization problem completely, but it caused a chaos with the channel capacity. But this is how it works. It just takes a clock, and the clock signal is just always goes up and down all the time, ticking. But instead of ticking like our clock every second, electronically it probably ticks 10 million times a second, and they use it all the time. And the good thing about it, they always tick exactly at the same length of time. So that's the good thing about those, the frequency of those electric signals at that level is that they probably make a second mistake in every 10,000 years or something. So the clock, electronic clock, is so almost so perfect. It takes a few thousand years to lose a second, maybe. So if we have data and the data needs to be transferred, the data is represented, as seen here, say 5 is represented, sorry, 1 is represented by -5, for example, and the 0 is represented by +5. So this data 10110 is represented in this form, but the clock up there is just continuous, and the operation happens by XORing those two signals together, and you end up with the actual, and there are two forms of Manchester encoding. So let's look at the top one. I don't know if you've done this, you should have done this, but you could do the XORing. It takes much longer, it's a bit more tedious. Or there's an easier way to do it in this Manchester scheme. In Manchester scheme, remember, because you XOR this with the clock, you XOR it with it here, and here you're going to get two values at every bit. So at every bit, it will guarantee you you'll either flip once or twice, at least once. That's going to always happen, and that's the idea in Manchester encoding, that we are always going to flip the plus and minus poles at least once every bit, and the bit happens every millionth, like a millionth of a second. You either flip in that million or you flip twice in that million. How does it work? If you want to calculate it, the idea is simple in this one. With 1, you always go from high to low. See this one? You always go from high to low. That's the result of your data and your clock. To do it, to confirm it, here's the one. Right in the middle of the bit, there's a flip. There has to be a flip in the middle of the bit. And if your data is 0, the flip has to be from high to low, from plus to positive to negative. And if it's 0, it's going from negative to plus. So that's the first step, you know, if you want to work out this. Well, at least that's the way I find it easy enough to remember. So if your bit is 1, it's going to be going from positive to negative. Now, let me just finish this. The second step that you need to take, they could be another flip at the start of the bit. Remember, those bits that's flips that I mentioned happen right in the middle. Right in the middle. See, the 0 here went up in the middle. With the 1, it went down in the middle. So the change must always happen in the middle. And now at the start of the bit, there could be a movement or not. There could be a flip or not. What will decide it? Will decide where are you now and where do you need to be. For example, if the next bit is 0, then you need to be at the bottom and you're going to go up. Or at the negative, you're going to go up. Well, if you are already in the negative place, don't move. You do the check here, right at the border between the 2 bits. Am I supposed to be up there? Well, it depends on the next bit. No, 0 always goes from negative to positive. I'm already negative, but then there's no change. Now, you go to the 0, but at the middle of the bit, you must make a change. If it's 0, it must go up. Now, this bit here comes to the start of the border of the bit. Will it go down or not here? When you look at the next bit, it's 1. In 1, you have to go from up to low. So I need to be up. I need to be at the positive. I'm already there, then don't move. Stay there. Don't make a change on the border. Now let me get to this point here. It's a good one. I went from 0. We have a 0, and I went from negative to positive. Now, at the border, should I go down or not? Well, it depends on what's the next bit. The next bit is 0. In 0, we always go from negative to positive. Am I at the negative place now? No, I'm positive. So I better go line myself up for the next bit. And in this case, I have to go down from positive to negative at the start of the border. Okay, get this point? Now, I'm here. Should I go down at this bit border? Well, the next bit is 1. 1 all needs to start from the high, from the positive. I'm already at positive, then don't go down. Stay there. Now, the last one here I look at, this one here, I am at 1. Just move down. Should I go up here or stay down at the bottom? Well, then the next bit is 1. The next bit is 1. In 1, you need to move from high to low. Well, in that case, I am low now, I better bring it up. So the change at the middle of the bit must happen. The change at the edge of the bit, sometimes it happens, sometimes not. It happens to facilitate the bit. If the bit has to go from high to low, and I'm low at the moment, well then I better go. I better make a flip at the start of the bit, so the middle of the bit will take place normal. That's how I remember it. That's maybe one way to remember it. You might be asked, most likely you're going to be given a string. And I'll give you a few examples in your tutorial, a few strings, and say, okay, then you plot out Manchester encoding using this technique. And so there it is, 0 is from low to high in the middle of the bit, and if it's 1 is from high to low in the middle of the bit. But at the border of the bit, you need to prepare it. Do you need to bring it up or change its place or not? Yeah, go on.
So it only works if the sender and the receiver both have the same clock.
They do, the receiver has to work it as well. See this one, this is how to join the 2 signals together. And that's the outcome, the result. The receiver, so now the receiver gets 2 joint signals, and they need to also split them. And there's another, a similar scheme where it will give you the output of the result. But this is just a logical kind of thing we make up to define the diagram. It's not electronically, it's done with XORing or, with another logical operation. Okay? Okay, so let's go past Manchester encoding scheme. differential Manchester encoding. This is the one that actually takes the two readings, multiple readings. So we're going to leave that. Signaling rate, how many bits are we going to transfer, and what's the user data rate. So we should not be sending any more data, but in Manchester encoding, it ends up sending a lot more data than the user data requirement. Long distance transmissions, Manchester and differential Manchester, not suitable for long distance. Okay. Clocking is always a problem. You know, using a clock is great, but clock cannot be used for long distances generally. So Manchester encoding, even though it doesn't solve the problem, but it's not practical at all to use. So the alternative is to use the bipolar AMI to avoid the long sequence of ones and zeros, which results, or zeros. We can't do both. But then we should use scrambling to solve the remainder long string. So the bipolar, let's use the bipolar that alternates with the ones. But if you have a long string of zero, that's still a problem. So the bipolar scheme only solves the bits that have the value 1. Even though, you know, that's not a correct statement, it can solve the other one, but it solves one of them, and we're going to go with solving the ones. So we leave the zeros for scrambling to do. So scrambling, let's see, how does scrambling work, and how does it actually solve a problem at no extra cost? So, after using the bipolar AMI with scrambling, after introducing scrambling, there are no DC components at all. Because the bipolar solves the DC component for ones, scrambling solves it for continuous zeros. No long sequences, we're not going to have any more long sequences transmitted of ones or zeros by those schemes. No reduction in data rate. We're not transmitting any more data than the original data. It's just we take 8 bits of zeros and replace them by other 8 bits. And we'll see how that happens. And we still provide the error detection that the bipolar AMI provides. So this is probably the best scheme so far. It provides error detection, it provides good capacity of the channel, does not waste any part of the channel itself. It's not complex, there's no complexity, there are no clocks, there are no extra devices that need to be, you know, installed or added to the devices. And it works. So let's see how it works. Now scrambling, there are 2 methods of scrambling techniques, unfortunately. You know, they standardized everything except scrambling. It didn't get to be standardized. So we have one method used in America and Canada, and one method used in Europe, or in general. So there are 2 techniques. One of them, the Americans, they say, okay, we can live up until about 7 bits, no more. 8 bits, we will not allow 8 bits of zeros. So it just keeps looking at the data going, as long as 3, 4, 6, 7, doesn't do anything. It finds 8 or 15 or something, it grabs 8 of them and changes them. In Europe, they say, no, even 8 might be too much. It can cause problems, so they reduce it down to 4. So they allow only 1, 2, 3 of zeros, but in the 4, grab it. If there's more, take 4 at a time and work on them. And the Americans, let's say if there are 20 zeros, it takes 8, does its work with it, send it, take the next 8 and the next 8. So it only deals with 8 until there's less than 8 left, it just let it go. So these are the actual. So let's look at the American technique. This is known as B8ZS, bipolar 8 zeros, or something like that. So that's how you remember it. So what they do, the Americans, they take, well, this technique, they take the 8 zeros, remove them, and replace them with 3 zeros, And either they go a plus or a minus, depending on the last plus or minus, plus value 1 was given. So if this 0 was preceded by an octet was positive, then we go positive again, which is against the rules. They say, remember, with the alternating, if we get a 1, we go, say, plus, and then 1 minus 5, or plus 5. Let's say now it's plus 5. Now we got 8 zeros. I say take 3, put the 3 zeros, and then go up to plus. We've already, if you were a plus, go plus again. And this is against the rules. This is, the receiver will say, hey, there is an error. But the way we give it this sequence here, in particular, if we say, go zeros, put 3 zeros, and make an error, kind of, we intentionally introduce an error, and then correct movement by going to the minus, and then go 0, and then make another error. So now we're making 2 wrong moves in the same 4 bits, and the receivers will say, oh, right, no, this means this is not an error, this was intentionally introduced, now I'm going to move them, and in my data, I'm going to replace them with 8 zeros. So it takes all those 8. So let's look at, it's easier to actually look at this. Now, let's look at this scheme here, this example here. Let's say this was the transmitted signal. We have 1, 1, and we know now what the last one, and then suddenly 1, 2, 3, 4, 5, 6, 7, 8. So now this scheme, the 8-bit bipolar 8 zeros, we found 8 zeros. If it was 9 zeros, we'll just take the 8 and ignore the other 0, we become a normal one. But now we're going to take, I keep forgetting this is sorry, this is a touch screen. Okay, so we take those 8 zeros and we're going to do this movement onto them. So this is what we do. We look, come on, where's my indicator? Let me see if I can get here somewhere where I can actually change the pointer here that you can see. Oh, that's not there. Video settings is it? No, I'm gonna now waste a bit of time. Leave it now. Find out later. Yeah, you can see the pointer, I think. Okay, so now those 8 zeros, it says replace them by 3 zeros. Here are the 8 zeros. We replace them by 3 zeros, and we're gonna give the wrong move. They call it here a violation. So you're breaking the rule. You're violating the rule that, hey, you should be, the last one was -5. We should have +5, but now intentionally we introduce a violation. So we go -5, and then a normal bipolar, that means from minus to plus, and then we go 0, and we introduce a second violation, followed by a normal move. So those movements here are special code to the receiver to say, really, that those 2 violations we made, followed by 2 correct movements, preceded by 3 zeros. That's just our code to say, forget about all those and replace them with 8 zeros in your memory. And that's how the American system works. It's beautiful, it's easy, you know, you always need to know what's the last bit. Was it a plus or minus? If you get a question and you were never shown those last 2 bits, you're only shown 8 zeros, then you need to, if you know the material, then you need to make an assumption. You say, okay, you didn't tell me in the question, was the last one before those 8 zeros, is it positive or negative? I need to know. I'm going to assume. And you make your assumption. You say, okay, I'm assuming the last bit was positive, and then you carry on from there. But it's zeros. This is the better way to remember it. This is 3 zeros, violation B0, violation B. That's one way. So it always works, one rule. Rather than the previous page, they showed it, they said, depending on, is the last one positive or negative? There is it. There it is. It says here, hey, if the last one is positive, do this. Some people might find this easier. If the last one was a +5, then replace the 8 zeros with 3 zeros and a plus. That's where the violation should be, a plus. And then normal minus, and then a 0, and another minus, that's another violation. But if the last bit was a negative, then our first violation should be a -1. That's one way to learn it. Learn what the last bit is positive, then you're gonna go something similar with it after the 3 zeros. If it's negative, then you go negative. Or you go like this here, where you say, replace the 8 zeros with 3 zeros, violation, normal, 0, violation, normal. Okay, that's how the American system works. Let's look at the European. Slightly more kind of complex, well, slightly complex. Now the European looks at 4 bits of 0. If it finds 8, it will take the first 4, deal with them, then the next 4. And then, if they're less than 4, it will leave them. So in this case here, in this example, there are 8 zeros, so it's going to deal with the first 4. Just looking at the first 4. The American says, this European one says, replace the 4 with 3 zeros, followed by, it doesn't depend on the last bit, 1 or 0, it depends on how many bits since the last one. How many normal flips did we have since the last 0? In this case, it doesn't show how many, we just shows 2 here, but was the one before this a 1 or a 0? It's another little kind of issue. It says, if we are an odd number, if you have a normal 3 ones or 5 or odd number, well then, replace this with 3 zeros and a violation. And so let's stop at that. So if the number is odd, replace it by a number of zeros, an odd number. Okay, let's look now at the next 3 zeros. Oh, the next 4 zeros. So that's the first 4 zeros, replace them by 3 zeros and a violation. If now, starting from now, the last violation happened, the last plus or minus signal, they're 0, they're none of them. When we're looking now at those 4, right? Remember with the European, you take the first 4, you're finished with them. Now I take the next 4. The next 4, it says, right, since the last 0, here's a 0. Since the last 0, how many bits have we had that had a plus or a minus value? And it's 1. Oh no, sorry, it's a 0. We did not have a normal kind of operation. I think, okay, I need to follow this. So it's a 0. We have a 0 instead of whatever the number here. So we will, anyway, so in one case, you replace it with 3 zeros and a violation, and the other case with a normal operation, that means go opposite whatever there was. B means go normal by bipolar. The normal is alternating, alternate from the last one, 2 zeros and a violation. So that's why the Europeans will replace 4 zeros with either 3 and a violation or a normal 2 and a violation. And that depends. Let me read it again. How does it decide? To determine which pattern to use. Are we going to use the 3 with a violation or 2 with a violation? As far as I know, if you had to determine which pattern to use, one must count the number of pluses and minuses, yeah, okay, since the last violation, right? So, you count how many violations did we have, how many normal ones and zeros. Here, we assume, for some reason, they assume there are 3 ones. Okay, even though here there are only 2, but we don't know what's defined before this one. We're assuming before we got those 4 zeros, we had 3 normal changes. That's an odd number. So if we have an odd number of changes before, before this location, then we're going to have 3 zeros on a violation. And the way I remember it, if we have an odd number beforehand, let's have an odd number of zeros, which is 3. That's one way to remember it. That's at least how I remember it. But after the odd number of zeros, which is 3, we're going to have a violation. Now, we made a violation. There's a plus or minus. So now this is a minus 5 here. Now we got 4 zeros. How many violations were before it? Well, not violations. How many plus or minuses? 1. And 1 is an odd number. So, sorry. We didn't have a normal kind of operation, sorry. Not that, this is not a normal plus or minus, this is a violation. We had a 0, not normal plus and minus value. If it's a 0, we consider that as an even number. Remember, if we had 3, we consider it as 3 ones here. We consider odd, we replace it by 3 zeros. If we had nothing, or we had 2 or 4 or 6 ones before those 4 zeros, then we'll replace them by a normal operation and 2 zeros and a B. But I remember, if we had an even number, you're gonna replace it by 2 even zeros. Okay, you have to have a B before it and a violation always at the end. If before this point that we had odd number, 1 or 3 or 5, then we're gonna replace it by an odd number of zeros followed by a B. I don't know if it makes sense, but it has to make a sense. This question is almost a definite question on this method of solving the problems of continuous zero. This is what's supposed to be in addition to what you've done last year. This is the only part. Scrambling is the topic that we expect you did not do last year, and you should be doing it this year. So you might be getting a question on one of the other schemes, but this is almost, no exam has been around for many years without a question on scrambling, either the US technique or the European technique. So make sure you master them. The US seems to be simple, because you just look at the last bit, the last plus or minus. And based on that, you start with the violation, normal, 0, and a second violation. With the European technique, you need to know how many normal ones we had, normal changes, not violation. That's a violation that doesn't count. So for those 4 zeros, looking back since the last violation, since the last scrambling, we didn't get any ones, normal ones between this and the last bit. And therefore, we consider 0, that's an odd number. It's not an odd number, it's an even. And therefore, you're going to be replaced by 2 zeros, with a B and a B, between a B and a B. In this case here, we got 4 zeros, and before us, we assume here there are 3 ones. That's an odd number, then we're going to replace them by 3 zeros on a violation. If we had 5 ones, we're still going to replace them by 3 zeros and a violation. Okay, let's see if this makes sense. Do you want to have a little go at this? Or if you have a piece of paper. If you don't have a piece of paper, you don't have to do it. Or unless if I find some piece of paper in my bag. Just try it out on your understanding. And when you draw these in an exam, you need to have some vertical lines. Because if you just do them without vertical lines and try to get away with it, you don't. Like, I'm not going to assume you're doing it right. And you have the 0 in between or the 1 in between, it doesn't work. It needs to be. So the top one, the solution is already there. Okay. Right, the next one. But okay, this is good, just to confirm that you know this. This is what you get, 1 followed by many zeros. I assume there's a 0 before this. I should here mention maybe there should be a 0. So we know, well, in this case, it doesn't make any difference. What's the one before us? Is it positive or negative? So this one replaced by 3 zeros and a violation. So you get 3 zeros and violation is going upward. And that's what happens here. And a second violation here, there's normal operation 0 and another violation. And the receiver, once the receiver sees that, then they replace all these with zeros.
So like the number of 3 zeros is permanent in case of the US?
Yeah, in the US, yeah. 3 zeros, but the violation, it can be up or down. It will be similar to the last one. If this last one is up, then the violation has to go. If this last one was a minus, then this also has to go to minus. This goes up to high. You know, so let's look at the. See the difference between these two? So if this last one is negative, that's what your question was. So you get 3 zeros and a violation. That's gone down as well. Normal 0 and a second violation because that one. And normal. And that's what 1, 2, 3, 4, 5, 6, 7, 8. They're removed.
So between normal and
Okay, so I don't know. Let's go for the European one. No, not the European, the American one. Can you do this for the American one? The B8. Yeah. You don't have to give me these papers, it's okay. You don't have to do it at all, actually. If you're not in the mood, don't do it. You're not forced to do it. The other side for the next. You can do the European B8Z.
The what?
Bipolar 8 zeros. Replace 8 zeros. If you find consecutive 8 zeros here. So just you must find 8 zeros. 4s don't touch them. Go to the 8 zeros and replace them, and then we'll do the other one, the American one, the B4. The first 4 zeros, the Americans don't change, don't touch these. The Americans don't replace 4 zeros, leave them as they are. It's only when they find more than 8, they take the 8 and they replace them with the new, they scramble them. Okay, well, are you sure?
Yeah.
Oh, did I start it?
No, I think so.
Okay, I'm gonna reduce this a little bit. Hold on before people see the solution. Still there.
Can we take a picture?
Okay, just take it. Throw this or take a picture. I'm gonna remove it. Just to get the attendance, check the attendance. And I'll look at it for you. It's a plus and a minus, and the rest of them 4 zeros and a 1. Hold on, is that a 1? That couldn't be a 1. That's wrong. That's not the one. Consider that a 0 as well. That one is wrong. I shouldn't have drawn this. If it was 1, we would have done a positive, that's a 0. Sorry guys, that's a 0. Let me check this. Oh, no, okay. This is the sender wants to send it. No, you are supposed to work out the rest of it here. Including the 1, that's a 1. It's a 1 bit. Just keep going. What as a sender, what are you gonna make it? 1 or 0? Or a +5 or -5? But again, this is for the American technique. You need to plug all these here, including this one. Normally the zeros will be 0 values, but they're not 8. If we are going to be using the B8. And then the 1 should be the opposite of this one, alternating. But now we're going to have 8 zeros or 9 zeros. That's the one you need to replace the first 8 zeros. So now you're going to replace those 8 zeros, but this has to be +5. If we were using the 8-0 technique. Okay guys, so this should be a plus. I know I'm giving you the solution to this. This remain unchanged because you're a sender now. You have 4 bits followed by 1. The 4 bits don't change in the American system. The 1 has to go follow the rule. That's alternating, has to go up. Now the rest of it, you do the rest. 8 zeros. You only do 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. Only those 8 zeros. Don't. You might have to change this 0. I don't know. I don't think you need to change the 0. But okay, take the diagram. I'm gonna go into attendance and see if I can get attendance working. I'll be back in a second. Okay, attendance just not switched on. Now it is switched on, so. Okay, let's go back now to.
Like this.
Back to normality. Here we go. Okay, attendance is running now. Anybody finished? How did you scramble?
Sorry?
Okay. The first thing I'll change.
Okay, no list.
It's my relationship with the last one. No. Right. Okay, the code is, sorry, maybe you're right. Sorry, I think you're right. Okay, this is going to be a violation, so it's going to be positive here. And then those 3, 1, 2, 3, unchanged, and this one's going to be a violation with this one, so it's going to go up again. Well, both of them, the first one goes up, and the 4th 0 goes up, the next one normal, and then 0, and then another violation. Okay, let me see if the solution is there. No. Okay. The solution was for the European. I need that good solution, I'll put it there. Okay, guys. Let's just get out of this. This is the way this should work. If you got this similar question to this in the exam, this is the way it works. US, the bipolar 8 zeros. You go, there's no 8 zeros here, there are only 4 zeros, so don't touch the first 4. That this is in the 8-0 scheme. Now, this is a normal one. The normal one, it's an opposite of this one, alternating, so this has to go up. And then, now we see 9 zeros. So we're going to be working on the 8 zeros, the first 8 zeros. Only the blue and the green ones here. The normal signal was positive before those 8 zeros. So this is going to be replaced by 3 zeros and a violation. So this 4th zero is going to be replaced by +5, followed by normal, which is -5, followed by a 0, followed by another violation, which is another -5, and then normal or 0? Oh, normal, B, is it? The last thing, yeah. Okay? If you didn't get it, you need to revise your knowledge of it. Yeah.
What did you do by normal?
Pardon?
What did you do by normal?
The what?
What did you mean by normal?
Normal, that means it's not a violation. B. The code is B, that means by normal. The normal is if the last one is plus, the next one is minus. Or the next one is plus, the next one is minus. That's normal. No, 90, I haven't touched it yet. I just stopped at the last 0. What do you replace 8 zeros with in the 8 zeros?
0, 0, 0, 1, 1, 0, 1.
Okay. Why did you go 1? Because the one before it is 1, then you have to go to 1. Yeah. That's what I mean a violation. Normally we should, if the last one was plus, we normally do go plus. But when I say violation, that means go plus. Then we make it. And the B is normal. Followed by this violation, we go normal. That means, yeah, from plus we go to minus, or if it's minus, we go to normal. So the B is normal. Switch around. Violation, don't switch. If the last one was positive, go also positive. Okay, guys, so that's, if you've done the B8, maybe you should try the European now. Try the European scheme, the 4-bit. Yeah. There's maybe an assumption, let's say there are only 2, assume there are only 2 ones before the normal operation. Yeah? That's even. Yeah? Okay. So, all right. So this was 3. No, this should be a violation. No, sorry. This is the normal. Now we're gonna, these are the 8 change. We're gonna have 2 zeros. Normal operation. A 0, another violation. This one. And then normal operation. Okay, that's the code that we were in the previous slide. So you replace the 8 of them by this. Yeah, you need to memorize. Yeah, but there are 2 ways to do it. So you can either learn the 2 codes, or you just learn the code that says this one should be a violation. There are 2 codes. The one says if this was the last one before it was positive, then you follow this, and it was meant to follow another code. Or whatever this was, violated. That means go the same. Instead of going in the opposite direction, you violate the rule by going positive and then followed by a normal and a 0 by every value. Normal 0, and then go another second violation, normal to normal. That's the code. Memorize the code in any way you like, but you're given the question, you should be able to plot it. Now go for the European scheme that deals with 4 bits. So first, you're going to deal with these 4 zeros. And then you have a normal one. This is not, part of the encoding. So in this case, and before this one, we assumed there was another scheme. There were only two. Assume there are only two ones here before the normal work or operation. So these are going to work on the basis they were preceded by an even number of bits. When you finish with this, when you go to the next zero, there's a normal one here. So there's only an odd before those 4 zeros. There's an odd number. So work on the basis that they are preceded by an odd, which means you must replace by 3 zeros. Then this one, you assume there's nothing before normal, so 0, that's even. So you're going to replace it by 2 zeros with an annihilation. Okay, have a go and see how it goes, how it works. We'll have a tutorial, I'll give you tutorials to try them and hopefully you'll master them. But you need to do that. So in the European scheme, you need to do 3 groups now of 4. One is preceded by 2 normal ones. One is preceded by 1 that's an odd, and one is preceded by a 0 normal. What time do we finish up? 3 more minutes. Okay. Who's the first to finish? The right answer. I usually have a box of sweets here, chocolates. First to get the right answer we get, but not today, another day.
Next week?
Yeah, next week I'll have a box of chocolate, and if I give you those tutorials, problems, first to answer we get a prize. Anybody who finished, we get a Kit Kat. No.
He attempts it. He did attempt it. Happy that did it. But he did it.
Okay, anybody who's having any issue or a problem with this? Anybody who doesn't know how to start? We're all right? How are you doing? Show me how you're starting on this. I haven't even started. Oh, listen, we're going to be having accumulating stuff. Make sure you know it before you leave. All right. Okay, let me, have you take this diagram. I know it's difficult to take, but take it. I'm going to change this just to bring you the rule. I put you onto the rule thing. There it is. To determine which pattern to use, you're going to be using one of these patterns. Either 3 zeros followed by a negative or positive. It's actually 3 zeros and a violation, or a violation, 2 zeros and another violation, I think. I'm not sure. Depending on how many pluses or minuses, how many ones, it's the last violation. So if it's odd, then you use 3 zeros and a violation. And if it's even, you use violation, 2 zeros and a violation. So every 4 zeros, you're going to replace it by 3 zeros and a violation, or violation and 2 zeros and a violation, depending on how many ones before them. None kind of scrambling ones. So these are the rules if you're all right. So you're either going to have 3 zeros followed by a violation, or normal operation, 2 zeros and a violation. These are the only 2 options. 3 zeros and a violation, or 2 zeros, first B, 2 zeros and a violation. Depending on the number of ones is even, I mean, go for this one. You know, it's even because it has 2 zeros as well. If the previous number of ones is odd, go for this one, 3 zeros and a violation. That's the easiest. So let's go with the first one. So remember, you're gonna go 3 zeros and a violation or B 2 zeros and a violation, depending on how many ones before us. Now we have here 4 ones. How many ones before us? 2. So that means we're gonna have normal, 2 zeros and a violation. B 2 zeros and a violation. Right, we finished with that one. Now we have a normal one. I don't know. Hold on. That's normal, 2 zeros and a violation. Normal one, we go downwards. But there's only one. You have 4 zeros. They are preceded by one item only, one value, that's -5. That's odd. That means replacing with 3 zeros and a violation. So these are the rules. If you are preceded by an odd number, replaced by 3 zeros and a violation. If you are preceded by an even number, like in this case, even, replace them by normal, that's the B. I mean, if this was negative, go positive. If this was, the last one was positive, go negative. That's the normal operation. That's the B, bipolar, normal. Normal, 2 zeros, because this is 2 or even, go for the 2, the one that has 2 zeros. That's how I remember it. If the number is 2, 4, or 6, I go for the one that has 2 zeros. The first part has to be normal, and the second, the one after that is violation. Now this is the normal one. The last one was plus, then we give it a -1. Now the 4 zeros, there's only one normal one. So that's odd. And if we go in relation to the one that has the odd number of zeros. 3 zeros followed by up or down. Violation. So because this last one was -5, is going to be -5. Now, the last 4, they were preceded by how many normal ones? 0. There was nothing between them. This was just scrambling here. There's nothing normal like this one. That's a normal one. There's no normal one. That's the number of normal ones is 0. We consider that not odd. That's even. We consider the 0 even. So it's going to be replaced by the one that has 2 zeros in the middle. 2 zeros. So this one is going to be normal. Wherever this 0 was up, then we bring the next one down. And this is going to be violation. Okay. Good luck to you.